So, hi, I'm Simon Scott. To those who don't know me, I'm one of the intensive care consultants at the Royal and had the great pleasure of doing a thesis in recent memory, which apparently means I know something about stats. What I wanted to do today was just really what's called sort of introduction to statistics, and mainly around things related to ICU. So rather than huge population statistics, more about statistics that we may find useful and try and make it slightly simpler to understand, because ultimately the concepts of statistics aren't that complicated. It's mainly the language used that I find quite complicated, a bit like how medics complicate everything with Latin. So basically, if you have any questions, I have set up so I can actually see people, but I can't hear you because you're on mute. So you can just wave or send one of those that wave things through, and then or just interrupt. I don't really mind. Or if I'm saying something completely wrong, also do the same. Right, let's see if this works now. So yes, so we're just going to start off talking a bit about data, and as you can see, I've put a picture up of Dr. Williams's wine cellar. And the reason for this is that we're talking about the kind of data that you will get or that you do see when you're either doing a trial yourself or when you're reading papers. And essentially there are two broad categories of data. There's what they call quantitative, and in this case I put it down as continuous, so you can have quantitative discrete data. And in the middle, actually, if I do this, can you see the arrow? No, you can't, can you? How do I do a pointer thing? Anyway, and on the right hand side is the other kinds of information that you can get. So you have ordinal data. So what that is data that's organized in a hierarchy. So for example, EWS. So the important difference is that unlike continuous continuous data, you can't divide this up. So you can't have an EWS of 5.8 or 5.2. It's either 5 or it's 6. But the important thing is that there is some kind of hierarchy to it. And then there's data which has no hierarchy, which essentially, so for the right hand side, if you're thinking about what kind of scrubs, what color scrubs ICU staff like, for example, there's no hierarchy objectively. I mean, obviously blue is better than pink, but objectively, there's no, you can't say, yeah, that's definitely a better thing. And the reason it's important is the way you analyze it is different. And what you do when you're reading papers, you not certainly if you're reviewing papers, you're not infrequently see you not infrequently see problems with the kind of data that people are doing. So the thing to remember about statistics, pretty much all statistics, is that all the clever words, all the clever tests are really just talking about average. And statistics is really about comparing averages. The first complication with average is that there's more than one kind of average. So as you can see, it should be familiar to a lot of you doing exams. The average everyone likes and statisticians like is the normal average or the mean. So that's where you have data that's distributed in a normal way or parametric way or on a Gaussian curve. So the nice kind of bell-shaped curve where the mean is the parametric average, the median is the middle number of a series of numbers, or the mode, which is the most frequent number in a series of numbers, are all the same. And that's the kind of stats that people learn about quite early on. We'll talk a bit about now. And it's the kind of stats that people like because the models work, the tests work very well for it. In reality, data is rarely that clean, especially in medicine. And on the left-hand side, you see what they call negatively skewed, on the right-hand side, positively skewed. Fundamental differences is where the mode, median, and mean, they're not all on the same line. So the middle box we call parametric data, the others would be non-parametric. So first of all, if you're reading a paper and they're putting all this data in, the thing to think about is what are they using the right average and what average do they mean? And generally, the mean or the parametric average is fairly specific. to have a mean, the data first have to be continuous, and they have to follow a parametric distribution. And those are the rules. And actually that excludes an awful lot of information that we collect in research. Whereas the median data can be ordinal. So that means, as I said earlier, EWS scores, and continuous with a non-parametric or non-Gaussian distribution. And that seems to include most information. So when any study uses a mean, that's fine, but always question what is the distribution this average came from. And hopefully they'll have somewhere in the paper that will say it comes from a parametric distribution and we've shown this by blah, 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 blah. If they don't have that, then be a bit suspicious, because people like using mean rather than median because the tests are more sensitive. They're better, basically. The tests for normal distributions or parametric distributions tend to be better. Okay. So, and this is the kind of thing we're talking about. When you read a paper, there are other ways of knowing what they mean by average. So if you're talking about means, the paper should always include, and if you're writing a paper, you should include a standard deviation, which is a measure of the spread of the data. So the spread of the data, and I'm sure you're used to this image here, which obviously I can't point to, the one on the left, the curve. So 68% roughly of numbers in a parametric distribution will fit within one standard deviation. Two standard deviations represents 95.4% or just 95%, and nearly all the information, all the numbers are within 3 standard deviations in a parametric spread of data. And if you're talking about a non-normal distribution, instead of using means, you use the median, which we said is the middle number. And then people talk about the interquartile range. Now, the interquartile range is actually quite straightforward. You essentially split your data into quarters. And you mark a line at the 25% mark and a line at the 75% mark. And the interquartile range is what lies between 25% and 75%. So it's between quarters, between the bottom quarter and the top quarter. And then you have the median. And that's essentially, it's not the equivalent, but it's how median data should be presented. They should present the median and then present the interquartile range. And this graph on the right is a box and whisker plot. And if you look at studies, generally you'll see quite a lot of these. They're not just exclusive to non-parametric data, but they are used a lot with that sort of information. And there are different types of box and whisker. Generally, the box is the same. It's normally quartiles with a median, and the two little lines on the end with a joining line, they're the whiskers. They can be different. So they can be 90% to 10%, they can be 99% to 1%, or they can be the complete range. And outliers are anything that don't fit within a whisker. And I think before I go on, I probably ought to reiterate, the thing to remember about statistics is that it's actually just about looking at numbers. It's about looking at patterns of numbers. The numbers themselves have no meaning. We ascribe meaning to them, and the numbers may come from meaningful experiments, but when the stats tests are running, and when you're looking at the numbers, you actually are just looking at looking at digits. And all we're doing is trying to describe how those numbers are arranged, how they fall, and find out what is the most appropriate average. And then we add meaning to that. So I just think it's one of those things that it's easy to forget statistics, and it's easy to get confused, to think, oh no, it's showing all these people aren't very well. It's like, well, it's not. It's showing that what the stats are doing is actually showing you what the numbers are doing. Right. OK. So that's a bit about what we mean when we're talking about parametric and non-parametric, what we mean by mean and median. And stats, by and large, quantitative, frequentist stats is about average versus average. And what you're doing is just a test to compare the averages. And that's really fundamentally what most statistics that you'll see in papers are about. There are a few other things which I'll talk about, but that's the main thing. So this is a little kind of thought experiment I did, generated some data for. It's just illustrating how we compare averages. So on this slide, we have the alcohol consumption of ICU nurses per week. And on the right hand side, we have alcohol consumption of ICU consultants per week. So clearly some of my colleagues are drinking 22 units a week. That's probably a bit modest. And the nurses are drinking up to 17 down from 7 units. And as you can see, they are, well, I know they're parametric distributed because that's how I generated the data, but the curves are essentially roughly parametric. And what you would see, what you often see in papers is something like the bottom left-hand corner, which shows it's a bit like a box and whisker graph, but it's a similar sort of principle. It has the average as the black dots, and the lines are the standard deviations, one above and below. So nurses drink on average 12 units per week, plus or minus 2. So 68% of nurses will drink between 10 and 14 units a week. And sorry, I didn't talk about the standard error of the mean, did I? So standard error of the mean is essentially how well does the average represent a larger population average. It's not something that's often talked about, and it's not, I don't think it's hugely important, but essentially the closer to 0, the standard error of the mean, the better representative your average is of a larger population. Sorry, and consultants. So the consultants 10 units, standard deviation of 4, a CM 0.3. And the question is this difference between means a genuine difference, or is it a difference that you can just account for as a random event? And this brings me on to what probably the most important part of any sort of stats is the hypothesis. So statistics is really about answering a specific question, the hypothesis. The danger of the statistics is data trawling, where you just go through data and you generate loads of associations, but you don't actually have a question. And that tends to lead to hours and hours of work looking at patterns and finding p-values, but actually none of it's useful, none of it's particularly interesting, and it's very risky statistically to generate your question from the data rather than start with a question and answer that with data. So you need a hypothesis, and as is the way of statistics, you normally state your null hypothesis when you're doing statistics. And null is basically an anti-hypothesis. So it's, instead of saying there is a difference between ICU nurses and consultants and how much alcohol they drink, you say there is no difference. And this is where we come on to p-value. So what is a p-value? It's the probability of the null hypothesis being true. So a p of 0.05, there's a 5% probability. You're testing against a 5% probability that there is no difference. Now we tend not to talk very much about null hypothesis, but actually it's what statistics are based on. Now conventionally, we use 0.05 or 5% as our cutoff for statistic significance. It doesn't need to be that. And if you're doing things like gene association studies and some of the physics work, they've got p-values of 10 to the minus 7. And if you think about 5%, you know, if you said to a patient there's a 5% risk of death from this operation, you know, they'd be a bit concerned. We would consider that a high risk operation. but in statistics in medicine, we accept 5%. So that does mean that 1 in 20, and this comes important later, but 1 in 20 times, if you do the experiment 20 times, you'll prove the null hypothesis. Right. So now you're going to have to. I want people to interact. Right. So what you'll often see in papers is a load of statistical tests, which mean very little to anyone. So I thought you could tell me which one of these do you think is a real statistical test? There's only one that's real. Can people turn the speakers on and shout out an answer? Lester Royal, turn your speakers on.
Do you know if it's back tonight?
What do people think? I don't know what it is, but got a few votes for number 3, Simon.
What do the Royal think?
Oh, so it'll be okay.
We've all voted for number 3 as well because we don't understand statistics either.
Yeah.
Somebody's just no, it's number 4.
Okay, well done. Well, you're right. Absolutely, it is. I thought the Rio de Janeiro holiday spa test was the best one, but never mind. Yeah, no, you're right. It is. It is the Criscar-Wallace H non-parametric test. The point is, these are often ridiculous names, and they actually don't really mean very much. And when you're reading a paper, please just don't worry about what tests they use. The only important thing is, have they categorized the data correctly? As in, is it the right kind of data? And have they done a test? Have they analyzed it suitably? The actual specifics of the test don't matter. So it can be anything, they can call it whatever they want. But as long as the data is organized properly, presented in terms of their standard deviation or interquartile range, the test itself isn't that important unless you really, really enjoy statistics and want to argue about the finer points. I don't. Right. So let's get back to the boozers. So the questions you ask, what I would ask of the information is, what are the data? Well, they're continuous. How are they, or at least quantitative? How are they distributed? Well, I know they're distributed. There are tests to show the distribution, but I know because I generated the information. They're parametric. And then there's another question about whether they're independent or not. Again, it really, that's all about to do with your trial design. But essentially, unpaired experiments are where the two groups aren't related in any way. So ICU nurses, you ask them how much they drink, you go to your consultant, you ask them how much they drink. They're both independent groups. If you took the nurses and said, this month, how much did you drink? And 3 months later, you said, this month, how much did you drink? That would be paired because you're comparing the same group twice. Does that make sense? Anyway, so I have no idea. So are they independent? So yes, they're unpaired. And so the right test for this is some form of parametric unpaired test, and the common one is a t-test. Dr. Little wants to know, what about if an ICU consultant was married to an ICU nurse? Well, I think they're probably multiplicative. So I think you'll find you're probably drinking vast amounts of alcohol. Okie dokie. Let's go on to the next. So the results of this, and I did this test. So on average, ICU nurses consume 12 units of alcohol per week, compared with the consultants who consume 10, and there's a significant difference in alcohol consumption. So, and you got a really impressive p-value there. The confidence intervals are quite small. People familiar with confidence intervals? Essentially, it's 95% you are, as the statistician, 95% confident that if you did this experiment again, you would find the mean would be between 1 and 2.3 units. So 1 unit, so if you did the experiment again, it might come up with 1 unit, another experiment again, it come up with 2.3. You're 95% confident that's where the mean of the experiment would lie. Okay. Now this is, I think, probably, so the hypothesis testing is really important. The second most important question about any paper you read is, so what? And there's content, a number of papers I've read where I've said, right, brilliant, but so what? So there is a significant difference in alcohol consumption. It's 1 glass of wine. Big deal. Probably easily accountable for error in your design, self-reporting and things like that. And you'll see this a lot, especially around, I always say in papers involving pain scores. People always have all these pain scores and say, yes, we reduced pain from a score of 6.3 to 5.2. And you get, so this is what I'm saying, the numbers, you look at the numbers and the numbers show you there's a difference between the averages. What the numbers don't tell you is the relevance or clinical significance of that change. So whenever you're reading papers and you're looking at things like stats, a really important question at the end is, so what? And this is a really good example of that. Right. Okay. I'm going to run out of time for counting this. Okay, so errors. So why do we do stats? Well, we do stats for the reason is that we want to demonstrate that we want to demonstrate that these are genuine findings, that they're not occurring by random chance. So in EOLIA days before stats, you might say, 12 units of alcohol is bigger than 10, therefore that's significant. What stats do is try and show, well, actually, yes, it is numerically, there's a statistical difference. It's a genuine difference. There's only a 5% chance. Sorry, there's only a 5% probability that this difference occurred by chance. But the other type of error, and the one that is very common, particularly in critical care research, is power. Well, it's type 2 error, which is relates to the power of a trial. And generally, type 2 errors are finding a negative result, as most ICU trials do. Ever read papers? There is no significant difference in the outcomes. It's always the same in ICU trials or the second trial, but the true result is positive. And we obviously don't know the answer to that always. So what we generally try and set, we try and have an 80% power in studies to detect a genuine difference. And there's a whole thing about power analysis, which is slightly complicated. And if you're going to start your own trials, you have to have some idea of what you need. But the long and short of it is that the more individuals you have in a trial, or the bigger your sample size, the more likely you are to avoid a type 2 error. So large sample sizes means that you're more likely to see a genuine result. And so if it's negative with a large sample size, then you can say, yeah, actually, that really is negative. But you'll see in a lot of studies, people will say, we found no significant difference. We believe a bigger trial is needed to demonstrate whether this is true or not. And we can do another talk about sample sizing at another point, but for the time being, that's one of the kind of key concepts. So you'll often hear people say trials are underpowered. Conversely, you often hear people say, oh, well, this trial only had 20 patients in it, it's not relevant. And well, actually, it may be, because the statistical test, if it comes back as positive, if it comes back with significant difference, it doesn't necessarily mean, it doesn't 100% mean that trial was right and that there is a difference, but it does mean within that small group of patients there was a difference. The example I give is if you line 10 people up at the edge of a cliff and start pushing them off, do you need to get to the last person to know that falling off a cliff is bad for you? You probably don't. And that's a little bit if you've got a very, very strong, very powerful difference in something like survival, you don't need an enormous sample size to show that. The issue becomes when you're trying to make that sample size representative of the general population. So if you're pushing those 10 people off the cliff, and on an island next to you is people made of rubber who won't get hurt, what you've done to those 10 people pushing off the cliff, you can't apply to the rubber people. It's a slightly esoteric example, but that's generally the idea. So sample size is important, but you also have to think about it in terms of what the study has shown and its relevance. Right, let's go on to other data. So that's what I've done is talk about parametric data, having started talk saying is actually not that often we see parametric data. But the non-parametric data is essentially analysed in a very similar way. It's just the tests have got different names like Kruskal-Wallis and Wilcoxon-Rank-Sign. So it's very similar. Non-parametric data, the examination is very similar. Hang on, excuse me for a second. Sorry, I've got this ridiculous dog. So yeah, so your statistical tests are generally less sensitive as well. The next bit really about what do we do with data that it doesn't follow nice patterns. It doesn't follow a nice histogram, nice sort of histogram, giving you nice curves. So categorical data or data that's non-continuous. So there are a few ways of doing it. Now, one of the nice things about continuous data is that you can transform it into non-continuous or categorical data. So let's say you have a drug called Asleepolol, and you have a non-anesthetic drug called Bedtimonone. If you can measure how long it takes to put people off to sleep. So I'm a bit distracted by this puppy is being annoying. So you can time how long it takes for them to go to sleep. But we can also do saying, well, what do we actually want to know? I want to know, will they fall asleep within 1 minute? And you can divide your answer, you can categorize it into within 1 minute. So it takes up to a minute or more than 1 minute. And it makes it quite a nice way of analysing data. Because the clinically relevant thing for you isn't necessarily the average time, it's actually how many of the patients go anaesthetised. I want to know 1 minute, but you could do 20 seconds or whatever. So, and like all tests, you would do a null hypothesis. The null hypothesis being there is no difference between drugs and inducing anaesthesia within 1 minute. And then you do a test. Now, generally it's chi-squared, or for small numbers and 2x2 tables, tend to use Fisher's exact, which is very similar. And you get a p-value, but you also get something called relative risk, which again is something for another talk. But fundamentally, what it shows that Asleepolol is 1.5 times better than Bedtimonone for inducing anaesthesia within 1 minute. So that's essentially a way of analysing. That's really data with a binary outcome or categorical data. The other thing people often do in audits. Copy. What they do in audits is that they collect a lot of information. And then come to someone like me and say, what stats can I do on this? In fact, I remember doing that as a trainee. And for example, we talked about scrub colours. So you collect information about the favourite scrub colours amongst 100 ICU staff, and this is the results. These are the results. And someone wants to know, well, how is blue choice significantly greater than the others? The thing about this kind of information is that it has no order to it. You can't, so, as I said earlier, blue is not objectively better than red or maroon. You can't fractionate it. So you can't have a bit of blue and a bit of green in the scrubs. And it doesn't have a distribution. And interesting, this is where the average mode comes in. And mode is how you describe the average for this kind of information. And there are essentially, there are some, but there aren't really any useful statistical tests, certainly in clinical use for comparing modes. Well, yeah, we'll come on to that. So this sort of thing, there isn't really a test you can do. You can't, because you can construct your trial differently to get you information that allows you to do a test. So you could rank people's choices. So someone said, if you were to do this audit, and you sent out a ranking scale, so between how would you rank your colours and least favourite to most favourite. If you did that, then you would get possibly enough information to do some sort of testing. But what you can do is you can use contingency tables, which are remarkably useful things, to do an observed expected analysis. So for example, like this, you might say, this is on the actual count, that's what you measured. And you ask the manufacturer to say, well, what proportion are bought? What do people tend to buy? And it gives you proportions on the right hand side. And because it's 100 people, you can act between the two. And what you can do is then analyze your distribution of colours against what you expect from sales figures. And you would then conclude the local choice of colour scrubs is different from an expected distribution. And this is where you can use chi-squared tests. I won't go into detail of how to do a chi-squared test because A, I can't remember, and B, it's not very important. All right, who's that? Yes, Martin, you would. You look like a pink angel. Right. So moving on to something else related to contingency tables. So this is one of these this is about a concept I constantly get my head confused by. And it's all to do with sensitivity and specificity. But there's been a sort of small little virus that's been wandering around the world recently that's led to an awful lot of people becoming experts in COVID, in testing, and COVID testing particularly. And there's an awful lot of nonsense being written and said about it, particularly about the accuracy of tests. So partly because I constantly get confused between sensitivity and specificity, and I always have to keep reminding myself, I thought it might be worth spending a few minutes on it. So this is where you can use contingency tables to help understand what people mean by sensitivity and specificity, and this is how you generate the data. So first thing, sensitivity and specificity is assessing the quality of the test. It isn't if I have a positive test, what's my chance of having COVID? That isn't what sensitivity and specificity tell you. They tell you is how good out of a group of people with or without COVID, how many times will the test positive or negative? Now, normally you use gold standards, and we don't have a gold standard for COVID really. And it is an issue, the lack of gold standards, and you'll find this in medicine a lot. They'll claim a gold standard and compare it against a gold standard, but the gold standard itself is flawed. I think those at the Glenfield probably, cardiac output monitoring always seems to be compared against Swan-Ganz catheters. But I'm not convinced pulmonary artery catheters are a gold standard for measuring cardiac output for all the reasons related to how you put them in and where they sit and how good they are at looking at left-sided pressures. So where you have no gold standard, that's when you start coming on to prevalence, but I'll talk about that in a second. So sensitivity. So I tend to remember either sensitivity or specificity as the true negatives or true positives. As long as I can remember one of those, I can work the rest out. Or if you're really good at visualization, you can visualize a grid. But the sensitivity is the question. What it means is of patients with COVID, how many of those had a PCR positive test, or what proportion of the PCR positive test. So it's A over A plus C. So of patients with COVID. Specificity is the true negative, and the corollary of that's false positives. So what you're doing there is you're saying of patients without COVID who had a PCR test, what proportion were negative? So that's D over B plus D. But people don't use tests like that. People say, this is a PCR positive test. What's the likelihood that person actually has COVID? And people start talking about sensitivity and specificity at that point. And that's why I keep seeing written papers and things. Newspapers. So what you're actually talking about is the positive predictive value. And what that question is different is saying of the positive tests, so not of patients with COVID, but of the positive tests, what proportion had COVID or not had COVID? And so you've got A over A plus B, and similarly for the negative predictive value, the probability of testing negative in the absence of disease, you get C over C plus D. Now, does anyone have any questions about this? Because I'm going to show you some numbers in a minute to hopefully make more sense. But this used to confuse the heck out of me, and I always forget it. Is there any questions about this, or am I just the only one who gets confused? Yeah, it's quite possibly true. Okay, all right. So we can put some numbers in this. So most of us will be aware that the sensitivity of the COVID PCR test is around 70%. Some places have it higher than that, some places have it lower. And the specificity, So the true negative rate, or the true negative value is 0.95. So it's very specific, not as sensitive as we would like. But actually of more relevance to us is the positive, usually clinical relevance, the positive predictive value. So if a patient turns up with a PCR positive test, their pre-test probability, just looking at the numbers, would be 0.98. So you say you're 98% positive. So positive test is a 98% likely to have COVID. And the negative predictive value, so the probability of no disease if negative, is only 0.44. So a negative test isn't so good at saying you don't have the COVID. Now there's a really important caveat to this, and that's this pre-test probability stuff. And there's a thing called Bayesian analysis, and I think that's going to be mentioned in one of the papers presented later. But essentially, what it's saying is that the prevalence of the disease or the state of your symptoms. So how confident are you that someone does or doesn't have COVID before you do a PCR test? And this has a huge impact on whether it's likely the patient has COVID or it's unlikely the patient has COVID. And I'll show you. So this current slide shows you if the prevalence or the pre-test probability, so someone comes to you, they're coughing and spluttering, and you know the prevalence is high in society, and say, right, I think there's 80% probability that they have COVID, then the positive predictive value is 98% and the negative predictive value is 44%. If that pre-test probability drops to 20%, as it might be with asymptomatic patients with a prevalent but not overly prevalent disease, which is kind of the phase we're entering in, the positive predictive value drops to 0.77, so 77%. So if someone comes with a COVID test that's positive, you're actually now only 77% certain they have COVID. And if the pre-test probability, if the prevalence drops to 1%, then the numbers just get ridiculously small. But your negative predictive value goes up. So you can say, well, they've got a negative test, and now I'm 92% certain that they're negative. But the point is, it shows you all this talking about the usefulness of screening and PCR testing is entirely dependent on the pre-test probability. And it's a big issue for asymptomatic patients. How do you manage asymptomatic patients with a positive test? Well, currently you quarantine them. But let's say the prevalence goes down to 1%. I can't remember what it does to the positive predictive value, but it drops it down to around 8%. So they've got let's say they've got a 92% test of actually not having COVID, but they have got a positive test. Do you still put them in quarantine for 2 weeks? So these are big questions that we don't have answers to. And it is a big issue because the prevalence of this disease changes every 2 minutes, depending on which government's in charge and who's locking down where. Okay, this link here at the bottom, if you're interested, is really good explanations where a lot of these numbers come from. It allows you to play with the numbers to see what happens as prevalence changes, or to see what happens if the sensitivity and specificity of your test is different. I mean, that's the other thing to bear in mind. The sensitivity and specificity of the PCR is slightly dependent where you are, which lab it's using at. And I hadn't realised, I don't know if anyone understands cycle thresholds, but they're using very, very high cycle thresholds as a proof of positivity. They're using cycle thresholds of up to 40, which is not what, certainly with the RNA stuff I've done at lab, we wouldn't accept. Anyway, that's another discussion for another day. Any questions about that? Bueller? No? Okay. So, and the final thing I just want to talk about, because it's come up in a lot of papers, and I'll just be a couple of minutes on this and then I'll shut up, is logistic regression. It comes up time and time again in ICU papers, partly because of the kind of patients that are studied in ICU, but a lot of what we do is looking through data, trying to work out associations and correlations. So logistic regression is an example of data modeling, hence the model. And it's a form of retrospective data modeling, and is used to predict, to give you a probability of a binary outcome, dead, alive, filter, no filter, pain, no pain, based on variables you're interested in. So simple logistic is one variable, one binary outcome. So for example, passing an exam, what the test does essentially, it looks at people who've passed or haven't passed and associates it with the number of hours they studied. And if I give an example, let's say passing the FRCA, these aren't real data, so if you've done fewer hours on this, don't worry. But you can use it to say you can associate the number of hours spent working over a 6-month period with the probability of passing or failing. So it's more useful than, for example, a p-value on its own, which will give you a cutoff value. This actually gives you a range of values where you can say, right, I've done this many hours, what's my probability of passing? And essentially, so it draws this logic curve between the not passed and passed, and it gives you an odds ratio. And what that means, what that is the problem for every extra hour worked, how much does your probability, or how much does by what factor does your likelihood of passing increase for every hour worked? And these sort of graphs you get. So for example, if you want to know, so to have a 75% probability of passing, you would need to do 355 hours work. And as I say here, you can actually then put numbers into the model and say, well, if you say for 600 hours, you have a 99% probability of passing. But if you study for only 100 hours, you have a 3% probability. So that's why logistics are quite interesting and can be useful. They're only as good as the model, though, and the model's only as good as the data you put in them. And the thing you see in ICU a lot is multivariate logistic analysis or logistic regression. So let's say you want to look at hours, but also people say, well, look, you know, you work lots of hours, but maybe you drank loads of coffee, or you drank loads of alcohol, or you ate loads of cake just to keep you going. Surely those may have been influenced you. And so what you look at with multivariates, you take these, what they call covariates or variables, put them in, do your test, and it tells you the independence of each of those variables. So it says the difference between finding an association and trying to make a correlation. And so the results of the one I did shows that coffee, cake, and alcohol, although there is a small difference in odds ratio, they are not significant. Their confidence intervals cross 1, and therefore aren't independently associated with improvement. But more importantly, your hours have stayed the same. The number of hours you work remains an independent. It's now not just an association, it's now an independent predictor. And as I said here, for every hour work, the probability of passing FRCA increases by 1.83. You see this sort of stuff a lot in ICU research because we all look at old charts. So it's just worth having even if it's just a general understanding of what they're telling you. Conversely, if you see a paper which doesn't do logistic regression and makes strong claims on retrospective data about associations, saying this proves that, I don't know, drinking one coffee is better than the other passing FRCA, but they haven't done any sort of independent analysis or to look at the independence of the factors, then you can disregard it. Pretty much. Right. Okay. So that's all I wanted to say. So just a few questions for you, really. I was planning on doing some more stats type talks. It depends how many of you are still awake. It's also, sorry, I'm being attacked by this dog. Also, whether it's useful. And if you wanted more talks, what would you want to talk about? So I can talk about how you design trials. We can talk about other types of analysis. We can talk about relative risk, absolute risk, that sort of thing. Or we can talk about the problems and pitfalls of statistics. Let me know your thoughts. Right, I need to stop talking.
Thanks, Simon. That was really, really good.
Thank you.
Anyone got any?
Just going to say, I've got a good way of remembering how to remind yourself about sensitivity and specificity. So I remember specificity as spout. So SP for specificity rules things out, and SYN for sensitivity rules things in. So a true positive and a true negative.
Yeah, that never worked for me because I'm not. For some reason used to confuse the hell out of me. But I know for a lot of people that's something that works really well. The only way I can do it is I can just remember one thing. I can remember one thing at a time, basically. But yeah, spin and snout is something I've heard before.
So I'm Yang, I'm one of the registrars, and I've got the easy job of presenting a classic paper, which is the EOLIA trial, and Eden's gonna present a Bayesian reanalysis of the same trial to illustrate how statistics can do wonderful things. So this is the trial that I'm going to be talking about. It was published in the New England Journal of Medicine in 2018. It's an ECMO trial, and we can't really talk about ECMO before we talk about CSER, really. So just to recap what happened in CSER. So CSER happened when I was a baby 15 years ago, comparing patients with severe respiratory illnesses. Either we transfer them to an ECMO center, which is in Glenfield, or conventional treatment. And that particular trial, which was finished in 2006, showed us that 63% of ECMO patients survived without severe disability, compared to 47% survived in the standard arm. But there were multiple criticisms of this trial, in that if the patients were randomized into the ECMO group, only 75% of them actually received ECMO. It was essentially a single center trial where the patients are only transferred to Glenfield. And if they were randomized into the standard arm, there was no standardized protocol. So EOLIA is essentially, they wanted to rectify some of these criticisms of the CSER trial. So the question they wanted to answer was, in patients with severe ARDS, does early initiation of ECMO improve mortality at day 60? So it's basically a French study with lots of French centers, but there were 2 American centers and 1 Australian center which also participated in it. And there were ECMO centers and non-ECMO centers who also participated in the trial. And the non-ECMO centers were defined as centers where they have lots of experience in dealing with patients with ARDS and respiratory failure. And plus, ECMO can be established within 2 hours of randomization. So they compared patients with severe ARDS, where they are randomized to either receive immediate ECMO or conventional treatment. The primary endpoint is mortality at 60 days. And there are multiple secondary outcomes. So one of the most important one is something called treatment failure, which means they either die or they cross over. So if you're randomized into the conventional treatment and you have to cross over to receive ECMO later, then this is defined as treatment failure. So I'll talk a bit about inclusion and who they recruited. So they screened 1,000+ patients and recruited about 200. They included patients with ARDS who were intubated for less than 7 days. And these patients should have a PF ratio of less than 50 for more than 3 hours. Less than 50 means less than, I think, 6 kilopascals. Or less than 80, which is less than 10 kilopascals for more than 6 hours. Or who have respiratory acidosis for more than 6 hours. All of them should already have their ventilation optimized, i.e. they're receiving more than 80% oxygen, they're on a small tidal volume protective ventilation, and proning and paralysis has already been done. And they've excluded the usual people, such as if they are children, if they've been intubated a long time, if they're pregnant, if they have a really high BMI, or they are on long-term oxygen therapy, or they have heparin-induced thrombocytopenia, etc. So patients are randomized into the ECMO arm and the control arm. So if you are randomized into the ECMO arm, you receive immediate ECMO. And this is VV ECMO, and they do a jugular femoral approach. If you're randomized into a conventional treatment, then you carry on the current standardized ventilation. So, and then now they try and standardize all the ventilation strategies. And there's a lot of them in the paper itself, but essentially that you're trying to maintain lung protective ventilation with 6 mils per kilo, limiting plateau pressure. And if you desaturate, there are steps that they have recommended for the clinician to take to improve recruitment. All patients in the control arm are encouraged to be paralyzed, prone, and inhaled pulmonary vasodilators are offered to most of them. Now, if you are in the control arm, you are allowed to cross over to the ECMO group if you desaturate to less than 80 for more than 6 hours, and the clinician feels that there are no irreversible multi-organ failure and ECMO might change outcome. So what do you think the results showed? Now, at 60 days, in the ECMO arm, 35% of patients died, whereas in the control arm, 46% died. And the relative risk that they've calculated was 0.4, 0.76, but it crosses 1 and a p-value of 0.09. So this was deemed as statistically non-significant. But they also looked at one of the secondary outcomes, which means treatment failure. Just to remind you, treatment failure means either they die, or if you're in the control arm, you have to cross over to the ECMO group. And treatment failure in ECMO is 35%, means 35% died. In the control group, 58% had treatment failure. And for this, the relative risk was 0.62, and the p-value was significant. So this was defined, well, this was determined as a statistically significant outcome. So just to show you other things which may or may not be significant. So the ECMO group has less treatment failure, but they have a longer stay in hospital. They have more days free of vasopressor use. That means the control group needed more vasopressors. The ECMO group had more days free of renal replacement therapy. That means the control group needed more dialysis. And obviously, the ECMO group required less proning, less recruitment, and less use of inhaled pulmonary vasodilators. So I think none of them are surprising, really. Now, looking at adverse events from the EOLIA trial, the ECMO group had more significant thrombocytopenia. They had more bleeding leading to transfusion, but they have less ischemic stroke, which I thought was slightly surprising. I'm not really an ECMO expert, but that was a little bit surprising to me. Now, looking at just specifically about patients who crossed over, so 125 patients were randomized to the control group, and out of them, 28% had to cross over to the ECMO group, and that's quite a large number. And the median number of days after randomization where the crossover was 4 days. They had a PF ratio of 50 at that time, which is 6 kilopascals, and they had an average median SATs of 77%. 9 of them had a cardiac arrest. 7 of them went on VA ECMO, and including 6 on CPR. And these patients who crossed over had 57% 60-day mortality compared to only 41% mortality among the non-crossover patients. So they have said that the hazard ratio for death, and they tried to do this by applying a statistical analysis, because just to go back to the initial primary outcome, it was done by intention to treat analysis. Therefore, it didn't take into account crossovers, but they tried to take into account crossover in terms of how it disadvantages the patients, well, the data in the ECMO group, by applying something called a rank-preserving structural failure time analysis. And they said that the hazard ratio for this adjusted hazard ratio is 0.51, but again, the p-value was 0.055, which is non-statistically significant, depends how you view p-values. Now, there are some limitations of this trial. Firstly, initially the trial was calculated for 20% risk reduction in the primary outcome, which is death, which is quite a big risk reduction. So the trial is underpowered. The trial was stopped early because when they recruited 75% of the patients they wanted to, it reached the interim analysis panel felt that based on statistical analysis, they have reached the threshold of futility. Therefore, they stopped the trial early. There's a very high crossover rate. There was obviously no blinding. It's difficult to blind these patients, really. They've only blinded the clinicians who did the analysis. And the recruitment was done over 6 years. I don't think that's surprising. And for the crossover patients, some of them received VA ECMO, and this was not distinguished. The author's conclusion for this study is that among patients with severe ARDS, 60-day mortality was not significantly lower with ECMO than conventional ventilation that included ECMO as rescue therapy. And I was quite surprised when I saw this conclusion, because there are some quite important data from this, which I felt that the authors didn't sell this paper very well, because I felt that it was underpowered, but one of the key secondary outcome endpoints showed quite a significant outcome whereby there is a significantly higher chance of treatment failure in the control group. So, I mean, if you're trying to sell a car, I don't think that authors are selling it very well. So I'm going to hand over to Eden to talk about a NEJM editorial and also a reanalysis of the paper.
So my name's Eden. I'm one of the ECMO fellows. This is actually not going to, I know this trial is about ECMO, but it's not about ECMO. It's just a nice example of how different statistics can make things look different and the pros and cons of this. I'm not an expert at stats. In fact, I'm barely a novice. Will gladly be rescued by Simon or anybody who knows more statistics than me, which is probably a lot of people. So that's great. I saw this quote the other day and I quite liked it. That basically there are only 2 endpoints out of any trial, which is, yeah, I already knew that, or I don't believe it. And I think that was true when the EOLIA was published. The believers in ECMO were like, no, that's not the correct outcome, that's not the correct summary, that's not true. And then the people who are non-believers were like, yeah, we knew that already, we didn't need a trial to tell us that. So we're not going to talk too much about the ECMO-y bit, more about the stats. So important things to understand the difference between frequentist, which is I think what most of us are commonly used to thinking about when we think about classic papers and trials that are being published, versus Bayesian statistics, which is becoming more and more common and you will see more and more of. There is a significant move away from frequentist stats that I'll come on to talk about later on. So to try and explain the difference, Simon's already done a great job of this, and I'm just going to re-go over it again with maybe a couple of slightly different examples. So frequentist statistics always has a null hypothesis that there is no difference. So even if you're trying to show, so you're doing a superiority trial, you think one treatment's better than another, your null hypothesis is that there's no difference between the two. So your starting point is that the relative risk is 1. Now, say I want to do a study that about flipping a coin, and I believe quite strongly that I'm more likely to get heads than tails because that's what I believe. In fact, I think I'm twice as likely to get heads than I am to get tails. So what I'm going to do is I'm going to do a trial to prove this to the rest of you non-believers that this is the case. So I think that I'm twice as likely to get heads. So based on that, I can do a power calculation. So the power calculation is how many times I need to flip the coin to prove my theory. So what's important there is how big the difference, so the effect size will determine how many times I need to do it. So if you're trying to pick up a massive difference between 2 treatments, you only need to do it, you don't need to do it that much. But if you're trying to pick up a tiny minuscule difference to convince people, you're going to have a large amount of data to be able to be clear and definite that small 1% difference is significant. But because I'm assuming, right, that we're twice as likely to get heads. So let's say my power calculation says I need to flip this coin 4 times. So I do that, and then 3 times it lands on heads. So the relative risk of that is 75% divided by 25%, so 3. So I've shown you actually that you're 3 times more likely to get heads than you are tails, and I've done my power calculation. It's exceeded what I planned. That's statistically significant. So now you can scrap everything you were told in primary school about heads and tails, and you know, I've shown you now, demonstrated convincingly by frequentist statistics, that this is true. You could do the same again with rolling dice. So if I say, what are the chances of me rolling 2 6s, so that we think, oh, maybe it's, you know, 1 in 36 chance of that. The frequentist approach again would be that there is absolutely no difference between me rolling 2 6s as there is in rolling any other combination, which sounds ludicrous, but that's the null hypothesis that we're setting out with. Even though you might, the Bayesian person will say, we bring your biases to the trial beforehand. You've got information that you use beforehand. So even though we know, you might think it's 1 in 36, that doesn't stop people going down to the casino and gambling. They might have, you know, they've got the prior knowledge that they're wearing their lucky socks, that they've already won, you know, on the raffle earlier in the day, and it's clearly their lucky day. So their chances of, you know, rolling a double 6 is much higher than that. Or you might have the pessimist who says, look at this luxurious casino. They're clearly raking in cash. They're stacking the odds against me. The dice are probably weighted, and that's not the case. So what frequentist statistics does is it says, I'm not going to say that the relative risk is 1, because I've got lots of information, or I might have lots of information beforehand that's going to influence the way I interpret that. And how we actually practice medicine is very Bayesian. If I tell you there's a, you know, if you get a troponin that's elevated, there's a 90% chance of that person's had a myocardial infarction of ischemic origin. So then I present a patient who's got a raised troponin, and I ask you if you want an angiogram and PCI and want me to call in the cath lab emergently. You'll probably then want to know a bit more about the patient. So if I say that they're 20-year-old, they were in an RTA, they had a collision, and they've had a traumatic blunt injury to the chest, you're going to say, well, no, actually, I don't want you to call in the cath lab. It's probably myocardial contusion in the context of trauma. So you've got your other information that is the fact that it's 90% certain that that person's had a myocardial infarct from ischemic origin based on the troponin. You've used your other information, your prior information about the patient, to contextualize that. So this is essentially what Bayesian statistics tries to do. So Yang's presented the trial beautifully, so I won't go over it again. So it's a multi-center randomized control trial. Does ECMO reduce 60-day mortality in people with severe ARDS? And as per the frequentist results, no, it does not. Now you can look at this graph on the right, and you can tell me that there is no difference. There is no mortality benefit. That's a load of posh. There is clear separation in those curves. What's the part of the problem with this is that the statisticians or the trialists went into designing the trial by saying, we expect that ECMO reduces mortality by 20%. And then based on that, they did a power calculation of how many people they needed to include into the trial. ECMO did reduce mortality, but not by 20%. It reduced it by 10%. And therefore, the trial was underpowered, and we cannot confidently therefore say that there was a statistical difference, because if I want to sell you a drug that I say reduces hair loss in patients getting chemo, it statistically does that. You don't necessarily just go out and buy it and give it to everyone, because it might statistically significantly reduce the reduction of hair loss by 0.05% of the population. And then it might actually only just slightly reduce the amount of hair thinning. So it doesn't tell you anything about the treatment effect size, the p-value. All it does is it tells you how likely for that trial design and that trial size that thing occurred by chance. And as you can see, unfortunately, they did stop the trial early, and if they'd continued, they would have probably reached statistical significance. So under frequentist stats, we're going to enter it saying the null hypothesis is no benefit, so the relative risk is 1. What Bayesian statistics says, right, we're going to use all the information we have beforehand to re-establish where our baseline is. And there's two ways we can do that. We can either do that using people's opinions and expert opinion and anecdote and just experience in general, or we can use prior studies. If there's lots and lots of good evidence, you could ask why do you need to do the study in the first place? So generally, you tend to go with more the reference priors than the data-derived priors, but you can use a combination of them both. And then you can say there's obviously a variance in opinion or the interpretation of the existing evidence, and not everyone feels as strongly as I do that ECMO reduces mortality. So we need to take into account of that, because otherwise I'm setting up the trial to be biased right from the start. So we're going to have a selection of opinions. So we're going to have a strong enthusiast, a moderate enthusiast, a skeptic, and a strongly skeptic person. And we're also going to have a minimally informative. And that is essentially, your relative risk is 1. I've got no information. I've got no idea. You could literally flip a coin. I've never heard of ECMO. I've never seen it. I don't know what it does. I have no bias entering this. I have no opinion. I have no experience. From this information, so the informative priors tend to come from publications by experts who've either commented on the trials that have been out there or their expert opinion. So it's from published information, data, and then it's sort of a computer program can generate a sort of a spread based on that. What you will see, however, so the trials data, which is on the right, so that is the CESAR trial and then a couple of observational trials looking at H1N1 data, that actually the relative risk is 0.6 roughly. And then if you'll look at the opinion, the thing based on opinions, they've mapped that out. So even the most strongly enthusiastic person still has only got a relative risk of mortality with ECMO of 0.6. So that is even the most strongly enthusiastic person does not believe it exerts more of effect than the treatment data has shown. And if you're strongly skeptical, the relative risk is 1, which is, I guess, fairly frequentist almost in its nature, which means nobody really thinks that ECMO generally in these patients with severe ARDS who failed conventional therapy kills. Now, obviously, if you put people on who don't need to go on or etc., there is a harm, but in this appropriate selected population, no one believes it is worse for your outcome. Now, just to explain this again a bit more, so this is just selecting out the strongly enthusiastic group. So our computer has generated this beautiful curve. You can get lots of information from this curve. So, for example, if you've got a very narrow, tall curve, you can be, I'm pretty confident that the relative risk is this. Whereas if it's a bit flatter, like you'll see some of them were, and more spread out, you might be like, well, there is definitely a benefit, but I'm not sure whether it's, a relative risk of 0.4 or 0.8. Like, I know there's a benefit, but I'm not confident exactly where that lies. So we can see something about the height. We can obviously see where the mean is, or the median. So that value, which is 0.774 here, is the relative risk for the strongly enthusiastic group. You can then say how likely, if you're strongly enthusiastic, is it that your relative risk is less than 1. So there's a 99% probability that your relative risk is less than 1. So there's a benefit with ECMO if you're strongly enthusiastic. You can then say, you can pick any relative risk cutoff and say how likely is it that it reduces your relative risk is less than X, and you can give a percentage to that. So you can use these graphs then to get that data. Now, the one in the top left-hand corner, actually the flatter curve of the two curves, is now the strongly enthusiastic curve. And then what Bayesian analysis does is it then, once you've got the results of your trial, it superimposes that data on top of your different curves and looks at the degree of overlap between these and comments on it. Does that sort of generally make sense? So now what we've done is we've looked at all of those individual curves based on whether you're strongly or weakly skeptic or enthusiast, or you've got no prior bias at all. And we've looked at the probability that ECMO reduces mortality. And you can see, so this, remember, the EOLIA trial set out with the ECMO reduced mortality by 20%. And you can see that that probably is not the case. No matter how enthusiastic you are, even if you're strongly enthusiastic, there is only a 2% chance that that is the case. However, what it also tells you is that if you are strongly skeptical, you are more likely, even if you're strongly skeptical and don't think ECMO helps at all, that more than likely there is at least a 4% mortality benefit, because you will see that number there. So strongly skeptical, 4%, there's a 63% chance, if you're strongly skeptical, that ECMO reduces your mortality by 4% in that group. So you've now created a table with a construct, and you can approach that depending on your interpretation of the previous information and your bias and your attitude towards the other evidence and the studies beforehand to interpret the study data. And actually, by Bayesian analysis, there is no doubt that ECMO reduces mortality, which is the real conclusion from the study. What it is not is it doesn't have a p-value of less than 0.05, which has been arbitrarily plucked out of thin air that we've dogmatically adhered to for the last 3 decades or whatever. But there is no doubt that ECMO does reduce mortality, but probably not by 20%. And this is how this trial should have ideally been interpreted. So the reason I wanted to go over this trial example was that there is going to be a move away from frequentist statistics. There's a big uproar in the statistical community. There was a commentary in Nature which was signed by thousands of statisticians and trialists that sort of wanted to do away with statistical significance, because we either do or don't do something based on a p-value without really understanding what the data tells us. As part of this move, in 2019, NEDGM published their new guidelines for publishing. So if you want to publish a study now in NEDGM, you probably should read this, because your trial design should probably focus on this. They do not encourage inappropriate use of the p-value. So there are times when it may be appropriate, and they would still consider that accepted, but it shouldn't be the blank. We shouldn't naturally go to frequentist statistics and do that blankly. So I thought Yoda's comment of do or do not, that is out. You can't just read the summary, the abstract conclusion, and look at the p-value and said, well, it was better. So if I gave this drug, I reduced hair loss, without looking at how much that was by looking at the spread of the data, just understanding the data in better terms. Because as you can see, you can have 2 trials that have the exact same effect size, and one is statistically significant and one is not, and you will either do or not do something based on this. So you need to understand the spread of your data. The other thing is that the p-value tells you that there is a less than 1 in 20 chance that your results have occurred by chance. Now, if you do enough studies, then one of them will be positive by chance. And in fact, if you look at that, Yang had a lovely picture with all the secondary outcomes. If you do enough secondary outcomes, there is a chance that one of them will have a p-value of less than 0.05. That is not based on the fact that it's true, but because you've done enough, you've done enough p-values that one of them is now one of these 20 and has occurred by chance. There is a correction you can do for this, which is very infrequently used. So we need to know about the variability, we need to know about the standard error, we need to know whether the result is actually non-informative or whether it is actually just a negligible difference. What is the information telling us? And also back again to saying it's about effect size. P-value doesn't tell you about the significance of the effect, like how big that effect is and how big that difference is. So NEDGM have advocated replacing p-values with estimates, which gives you an estimate of the effect, and then 95% confidence intervals. Now, Yang gave us the confidence interval and it cost 1, so it was insignificant, but you could see that an enormous proportion of that was on the other side of 1, was on the plus side of 1, and therefore it barely just crossed 1. And then you can then go in to understand and look at in more detail the trial design. Is it realistic that ECMO alone is going to reduce mortality by 20%? And then sort of think a bit more about the stats and take it from there. Now, I love this little cartoon, and so I'm going to give you a moment to read it because it's fun, and it's my last slide. Remember, everything that you do in clinical practice is Bayesian. You've got all your other information that you use to interpret your tests. And you are going to see more and more of this kind of statistics being published in trials, because there is going to be a move away from it. That's why I probably need some more lectures on how to interpret stats and trials, because, you know, we're all going to get very confused soon when there's no p-value to look at. All right, I think that's it. I think we're done. If there's a QR code somewhere.
Thank you. Simon's got a question.
Thanks, Eden. That was really clear.
Cool.
Very interesting. Well, Simon.
Eden, that's great. Thank you very much. And also the EOLIA thing was very interesting. I wrote loads of things down. I probably haven't got time to go through them. I think my understanding is that essentially one of the problems we have in medical research was a number of problems, one of which is clinical data is messy. So what you're collecting isn't always what you want, and the information isn't always entirely accurate, and there's loads of values missing, and patients don't do what you want them to do. So they'll be diagnosed with ARDS, and it turns out they don't have ARDS, they've got aspergillus or something. You know, there's always these variables that come in, and, you know, as one of the professors used to say, patients don't read textbooks. They don't do what they're supposed to do, which is very annoying. So that's one of the problems, it's a clinical thing. And I wonder, the problem with the ECMO trial isn't so much about the risk reduction, it's more to do with their diagnosis. So ARDS is a syndrome. It's the same as sepsis as a syndrome. There's no real proven gold standard diagnostic criteria for either of these things. It's a clinical syndrome, so it's going to be susceptible to clinical variables. So I think frequentist statistics work well when you have a clear diagnosis. The way you start having syndromes, it gets very complicated, because you don't know the relative influence of the various bits that contribute to the syndrome, that contribute to the diagnosis that led them to be recruited, if that makes sense. The other issue is equipoise. Very few clinicians have equipoise. So we all think when we're doing research, we don't know the answer to this, therefore we'll recruit completely blindly. And the truth is, certainly around ECMO, especially when, because I was, you know, unfortunately I'm old enough to have been around during Caesar. We know that there wasn't equipoise in recruitment, and it's the same in all trials. There isn't equipoise, so clinicians have strong opinions, and that's what Bayesian, to me, is trying to account for. Is trying to account for the clinicians not being truly honest or truly, you know, they haven't got a relative risk value of 1 in their brain, and that's what the Bayesian essentially is trying to account for. What else did I say? The other issue is using mortality as an endpoint. In ICU trials, again, we often use mortality as an endpoint, but what we conflate that with mortality being a consequence of the disease, but often it's not. Mortality is often a consequence of comorbidity. So a lot of people in ICU die not because the disease killed them, but because their comorbidity meant that they couldn't survive the process. And it leads to us withdrawing care, for example. So there's a lot of argument about whether mortality is a useful endpoint in ICU trials. And I think there's a very strong argument to say it isn't. What is a better endpoint? Well, that's up for discussion. But I think we have to be very careful about using mortality as an endpoint. What was I going to say? And yeah, so you mentioned, this is a really small point, you mentioned at the end, Eden, about we don't often correct for multiple comparisons. Is that right?
Yeah.
Yeah, well, we should do. There's a Bonferroni correction and various other corrections. And again, reviewers shouldn't accept papers which don't correct for multiple comparisons. ANOVA's one, for example, that has a really, you know, is often used for parametric testing of multiple variables, and there's a very easy correction to be done, and those trials shouldn't be published if they've not been corrected. And I think my final point, I am there, promise, is about p-values. You're absolutely right. People look at the p-value and don't look at anything else, and the p-value is just a small part of information. It's not the conclusion. It's what it is looking at the numbers, saying this is how the numbers are distributed, and if you compare them, there is a chance that happen, you know, may or may not happen by chance. But you're right, you need to look at things like confidence intervals. You need to look at the spread of the data. And that gives an idea of how the trial is set up, but also how difficult or how representative the trial is of everyone else. Trials which have very, very narrow confidence interval standard deviations are normally a very, very select group, because that's how you manage to keep them all within a small contained area, and therefore aren't as representative of the general population. So the p-value isn't everything, but I wouldn't disregard it completely. I think there is a role for both statistical processes. You just have to justify what your argument is using those processes. But yes, we do have a problem in science, is that we have publication bias. If you have a negative p-value, you don't get published. And that is a big problem. And that's something that's really for reviewers of papers to work on, is say, actually, does this trial give you useful information, even though what they're publishing as a p-value isn't important? Because it leads to what people do, which was p-value, it's got a name for it, p-scraping, p-value hunting. It leads to people doing the wrong test to find a p-value to get them published, and that is absolutely the wrong way to look at data. I have more I could say, but I think I'll leave it there. Thank you.
Martin?
Sorry, I pressed the wrong one. Hang on, somebody in the audience has got a question.
Why is you sometimes people why you sometimes confident and don't want to compare the two data?
Oh, okay. So there's a question from the audience, which is about, I don't know how to phrase it, the use of p-values versus the use of confidence intervals, and how they kind of, why you pick one over the other, and how how you use that information. Does that make sense?
I don't know who wants to answer that.
You.
Okay, so my understanding is the p-value is the probability that the null hypothesis is true, that there isn't a real difference. Okay, whereas confidence intervals are, you're 95% confident that the true mean, or if you did the trial again and again, the average will fall between those numbers. So it gives you an idea of where the average should fall, irrespective of whether there's a significant difference or not. So I can't fiddle with any of the slides, but some of the confidence went below. Well, it depends what the range you're looking at, and depends what you're looking for. But you can go from negative to positive, and if you're going to a negative value, it means that if you did the trial again, you may show harm rather than showing benefit. So if you've got very wide confidence intervals, it basically reduces your certainty that repeats of the trial will give you positive information, or information that you're trying to justify, or you're trying to present. Does that make sense? Does that answer the question?
There's nodding.
Okay, all right, well, that's good. Not falling asleep nodding. Just not nodding off.
Does anyone else have any questions or comments?
None from here.
I don't think there's any more from here.
Any ECMO comments?
Why the name of statistical tests so difficult? Name them.
Somebody's asked why statistical tests have to have such complicated names. I imagine that's largely around people's egos, isn't it?
Probably. You know, why do we call those medical conditions ridiculous names? Not that I can think of one off the top of my head, but you know, what's that, HLH, for example. I mean, why? You know, it's to do with precision, isn't it? It's to do with precise describing, and if you're a statistician, that's what you like. I mean, there are arguments for the way we conduct trials that the people involved in the trial should have absolutely nothing to do with statistics. And that's a very good argument, because statisticians like clean data and clean numbers. Matt Charlton probably attests to this, because he's worked with computer scientists, data scientists, and they really struggled with the information that Matt was giving them, because it was.
It's probably just start giving it.
Well, but the bits that you did give them was essentially filthy data. It just wasn't clean. It wasn't precise enough. And it is a real problem in medical research, especially looking at the kind of trials that we look at in ICU, where you have a homogeneous population with homogeneous disease processes that we can't define. The numbers aren't clean, and it's really hard to make those numbers come out in a pattern that makes sense. And so that's why we're not going on gut instinct and gut feeling, which is another word for experience or arrogance, depending. But yeah, they have long names because it's just being precise, I think.
Anyone got anything else to say?
Oh, hang on. One more question. So if you've got, I'll ask the question. If I'm wrong, then just correct me. If you've got a high positive predictive value, does it always have the associated opposite negative predictive value?
Yeah. Do they always go together?
Do they always go together? I'm not sure they do, but
no, not necessarily. It depends on this, because I have to get back to that.
It's that table, isn't it?
Yeah, exactly. So it depends on your values of A, B, C, and D, doesn't it? So they don't necessarily always go together in a way. I mean, generally sensitivity and specificity tend to be a bit inverted, and it's the same thing. Not positive predictive value, negative predictive value tend to be a bit inverted. Certainly your Bayesian influence on them, as in your pre-test probability, has a sort of inverse effect on them. But in of themselves, the way they're calculated would say that they're independent groups. So they shouldn't necessarily go together. There may be a tendency for all that to happen, but they shouldn't necessarily be the reciprocal or the inverse of another one.
Yeah, I suppose we don't see many examples where they're completely dissociated, do we? Because otherwise we wouldn't use that information.
Yeah, I mean, I'm not convinced we really do use any of this properly. I don't think we do use positive and negative predictive values very well. We always talk about sensitivity and specificity, but that actually isn't useful information in the main part. I remember as a medical student really struggling with this concept of, yeah, but what does that actually mean, sensitivity and specificity? What does it mean if someone comes with a positive test? What does that mean? And the truth is, it doesn't mean anything. What you need to know is what the predictive values are. But also, we add a lot to the predictive value, and this is the Bayesian stuff. We have a preconceived notion based on that person presenting. So like acute coronary syndromes, someone presents with a positive troponin, but they're 22, an athlete, got normal ECG, probably explain it away, because mentally you said the positive predictive value, the pre-test probability is very, very low. Therefore, the positive predictive value has been reduced down, and you tend to end up disregarding. You don't quantify it, but that's how you do it. Whether you should or not is another question.
Any more? No, I think everyone is now statisticked. I don't know what the word is. Statisticked out in the Royal.
I don't think it's a word, Simon.
Statisticulated, no, not testicle. That's a different word. Well,
It will be that a test is going to have a negative predictive value.
right.
Is it benefit to do that test? Or
So if you think a test is going to have a negative predictive value, is it worth doing the test? Well, I would argue yes, because if you think something's going to show that it's negative, it tells you that you shouldn't do it. Or not shouldn't do it, but it gives you that information.
Yeah,
Does that make sense?
More important often. So D-dimers is a real classic of that.
Yeah.
Ruling stuff out is actually really very, very important. Yeah, so definitely.
Depends what you're going to do with the information. It's the same as any test you do. You need to decide what you're going, whether it's going to change what you do or not.
There was a point I was going to make, which I haven't. It was based on what I said in the consultant meeting today, but it's about repeat testing. And again, it's an issue for for Jenny and stuff with COVID testing. So the idea is that you do repeat testing on people. So we know that the best labs, and I don't know what our specificity is, but the specificity of the COVID test is 95%. So we know that if you do the test 20 times on one person, 1 out of those 20 times I'll have a positive test. Sorry, 1 out of 20 times there'll be a false positive. So if you repeat test lots of people lots and lots of times, eventually you'll end up with a positive test just through numbers. And so we do have to be a bit careful about how we use these tests. Now, 20, people aren't like to get 20 tests, and obviously they may well also have they won't have, it'll be negative all the time. But the question does come, what if it's positive? And that's when you come on to your positive predictive value. Now, if the specificity is actually only 80%, then it's 1 in 5 times. So we need to know what our specificity is for here to give us a better idea of what we do with the information, of how frequently we test and the use of frequent testing. But it is a thing about stats. The more you do it, the more you test, the more likely you are to get a number you want. Which is why you have to be rigorous. Dr. Little's got something.
It was only in relation to that, is that if you were to repeat a test on the same patient 20 times, what is the guarantee that there isn't another variable that gives you that 5% chance of it not being correct? As in, if you were to repeat one test on 20 different people versus one test 20 times on the same person. And is that the same error effectively?
Yeah, I tried thinking about this morning. I got very confused. I think yes-ish. Because the way the tests are devised is based on a population. And actually the positive predictive value and the negative predictive value you shouldn't really use them at an individual level. You should use them at a population level. It's like Apache scoring and all that stuff. And yeah, someone just posted, yeah, it depends a lot on, well, that's more to do with the prevalence and stuff. But yeah, it's because the way the 95% specificity is not for one person, it's for the whole group. It's for everyone you've tested. And we know there are sampling errors, or the virus is not where it should be. It's in a different part of the body, which is probably accounts for that small 5%. So unless you do an individual and you individually give them COVID and run these kind of tests, you can't really say.
This was the thing I heard about my issue around the lateral flow testing.
Yeah,
everybody was saying, oh yeah, no, it will improve in how well it will pick it up the more you do it. It's like, well, really? Is that technique? Is that something else? Do the tests amazingly become better as you continue to use them?
Yeah, absolutely. So I was just going to answer Jenny's question as well. So Jenny, the pre-test probability mainly influences your positive predictive value and your negative predictive value. So it's saying if your test is positive, what's the probability of you having COVID? What it doesn't change is if you have COVID, what's the probability of you having a positive or negative test? Sorry, because Jenny wrote, yes, patient pre-test probability changes. It absolutely does. But in terms of the false, it shouldn't affect the false positive rate, because the false positive rate is a 1 minus specificity. I might spend a bit too long thinking about it this morning. But I'm also, I went around in circles and I got it wrong.
Doesn't sound like you.
But when I was putting the numbers in, that what seems to happen. If you go to that website, that BMJ thing, it is quite interesting if you're interested in that sort of thing, in fiddling around with specificity, sensitivity, pre-test probabilities and things, and showing how large an effect small changes make.